Back, let us continue our journey about instruction set architectures. Another aspect of ISA design is to choose what kind of data types to support directly. Almost all ISAs support different sizes of integers. The maximum size supported is often depending on the size of the internal register width, which in most high-performance processors is either 32 or 64 bits. When dealing with shorter data types, you need to take care when loading them into a longer register. For positive numbers, there is no issue, but if a 16-bit negative number is put in a 32-bit register, then in order to keep it still negative, the sign bit, most significant bit, number 15, needs to be extended and fill the more significant bits 16 to 31. Other data types that you almost always see in high-performance processors are addresses and support for floating point numbers. Occasionally, you can see support for binary coded decimal. This is a number representation where a 4-bit binary number is used to represent a decimal digit. Then you need special instructions to perform arithmetic on this data type. The x86 ISA and IBM mainframes, the Z architecture, are the only current ISAs that support BCD fully. The final data type that is common in modern high-performance processors are the packed vector data. It was first introduced in the Pentium processor with the MMX extensions, which let, for instance, an 8-byte sized integer occupy a 64-bit register, and arithmetic operations could be done on all 8 integers in parallel. We'll talk more about this in April when we talk about data parallelism and vector processing in GPUs. Part of the ISA specification, and perhaps even more of the application binary interface or ABI, concerns the memory and how it's addressed. Most processors support a byte addressable memory, but the CPU most often uses the memory in chunks. Between the core and the cache memory, the width is often 32 or 64 bits, and between the DRAM and the CPU, it's often larger. The CPU can put constraints on how a word can be laid out in memory. It might require that they are aligned in memory. Since the memory is addressed per byte and most data accesses are of larger items, we need to know how data is laid out in memory. This is part of the ABI and can be both processor specific and for each programming language. For instance, a 32-bit integer takes 4 bytes, and when you store it at location A, it will occupy addresses A plus 1, A plus 2 and A plus 3. There are two options. Either a 32-bit integer is stored with the most significant byte at address A, called big endian, or with the least significant byte at address A, which is called little endian. Another issue is if the CPU allows multi-byte items to be stored at any address, or if it has to be aligned to the size of the object. Many processors implement correct behavior when a data item is unaligned, but the performance will be significantly improved if a 32-bit data item is aligned at a 32-bit address that is ending with a 0, 4, 8 or so on. Furthermore, different ISA support different ways to address the operands. The table here shows some of the addressing modes existing in modern CPUs. Load store or register architectures have a more limited set of addressing modes than register memory architectures. These are marked in green here. This does not mean they are less effective. You need some more instructions to achieve the same thing, but these instructions can be implemented more efficiently, so the net effect is about the same or better. Then of course you need to decide which instructions to implement and support in the ISA. All ISAs need instructions for moving data, arithmetic and logic, control flow, and to some extent floating point operations for arithmetic on real numbers. CPUs designed to run an operating system also have system instructions allowing them to execute in different privilege modes, for instance system and user mode. Therefore, you need instructions that allow user mode code to call functions in the operating system, also called system calls. You need special instructions to implement virtual memory, return from interrupts and exceptions, etc. If you have special data types like BCD or vector data structures, you also need instructions to carry out operations on these data types. Control flow instructions require some extra attention. There are essentially 5 different types of control flow instructions that you need to understand for this course. We begin with branches, which can be either conditional or unconditional. A branch is relative to the address of the branch instruction. The instruction specifies the condition, if any, and a displacement or offset, which is the distance to the target address. In RISC-V, the branch offset is encoded with 12 bits, which are multiples of 2, as instructions can only appear on addresses which are a multiple of 2. The displacement can both be positive and negative and is sign extended and added to the address of the branch instruction to calculate the target address. The branch range is thus ±4 kilobytes. Historically, all jumps differ from branches in that they are not relative to the current PC. However, already with 32-bit addresses and 32-bit wide instructions, it was not possible to encode the full address and an opcode in the instruction. And with 64-bit architecture, it's really impossible. Therefore, in RISC-V, what distinguishes jumps from branches are that they are unconditional and the displacement is much larger, allowing for a 1 megabyte distance. In order to call a function or procedure, you need to remember the address where you came from. In RISC-V, this is done by storing PC plus 4, the address of the instruction following the jump, in register X1, also called RA. Then there is a specific instruction JRLR, which jumps to the address found in the register. Returns from exceptions and interrupts can be done in the same way, except that you also need to restore the privilege mode that was before the exception interrupt occurred. When deciding about an ISA, you also need to decide how to encode the instructions. There are 2 major variants: variable length encoding and fixed length encodings. x86-64 is an example of a variable length instruction encoding. The shortest possible x86 instruction is just 1 byte, and the longest possible is up to 15 bytes. This also means that instructions are not aligned in memory but can start at any address. In contrast, RISC-V uses a fixed length instruction encoding. Each instruction is 32 bits or 4 bytes. There is also a 16-bit compressed instruction set, which is optional in the RISC-V implementations. Since the compressed instructions can be mixed with regular ones, instructions are required to be aligned on addresses which are a multiple of 2. The choice between these 2 options is really a trade-off between the number of registers, efficient encoding, and ease of implementation. Most program examples in the course will be given in RISC-V assembly. RISC-V is a load-store architecture with 32 general-purpose integer registers and 32 floating-point registers. The encoding of instructions is not important for the course, but you should know that the encoding is fixed and that there are specific fields in the instruction that designate source operands registers and destination operands registers. Load and store operands have a source register specifying a base address with an offset to be added to this base explicitly in the instruction encoding. Load has a register as a destination and store has a register as a source. RISC-V instructions are written in the syntax operation, destination, source 1 and source 2.